All right, welcome to Lecture 9, Friday's class. This week we've been working our way through Chapter 5. And Chapter 5 is about the local analysis of three bifurcations, saddle node bifurcation, pitchfork bifurcation, and transcritical bifurcation. Then Chapter 6 is a shorter chapter, and that's going to be about the period doubling bifurcation. Okay? Let me kind of recap to you where we are currently in the notes. Okay, so we just had an update of the notes today, October 16th, and where I've put in problem set number 3. That's something that I was going to make an announcement for, but before we get to that, so just to remind you, we are still working our way through this Chapter 5, going through the different cases, case A, as it's referred to in this chapter, case A1, A2, and A3, for the three types of bifurcations, and we're hoping just to put an end to that today. And then finally, I think this will be addressed on Monday, this Chapter 6 on period doubling bifurcation. But the techniques between the two kinds of bifurcations, case A and case B, are very, very similar. Okay? Many of you did hand in your problem set number 2. This was due today, well, Friday, I think Friday of week 3. And then problem set number 3 should be up at this point. Problem set 2 solutions are also up, except that I haven't had time to put in yet questions 3 and 4, and I'm hoping to do that over the weekend. And so that way you can get it aligned also with your tutor comment. That will be made by Moodle. Okay, otherwise, any other announcements I wanted to make? Not really. Okay, this should be fun. So Saturday, 24th of October, I'm hoping, so I know that I've not done the best job in going through homework problems just because we've been so stacked with learning new things. And I've been depending on you doing your problem sets. But we're going to put aside Saturday, the 24th of October. I will do a live stream sometime in the morning, and I'm going to try to get through problem sets 1 to 3. So obviously, this is not a normally scheduled lecture time, but please do come by if you can stop by. And then as long as one person's in the room, then I probably can keep on going and get through all homework problems. After that, it will be uploaded on the usual Panopto or YouTube, and you can watch it there. It'd be very nice if once it's uploaded, I can somehow timestamp the different points where I talk about the homework problems, so you can see exactly, so you can refer to very easily the homework problems just by looking at the video and then pressing the timestamp item. But we'll see whether I have time for that. But please, if you can, remember, I'll remind you again next week. This will be next weekend. I'll do this for problem sets 1 through 3, and then probably in 3 weeks' time, I'll do the next 3 problem sets. And I assume that's going. Yeah? I don't know what time it's going to be. Basically, what time am I going to wake up? That's the question. I'll make a decision of what time it's going to be, because I have to do it at home. I'm going to have to drag a lot of this stuff. I think I'll want to do it at home because I don't want to come to the university on a Saturday. That would depress me even more than having to do an extra session. So I'll do it in my kitchen. Wouldn't you prefer to do it in the morning? And that way you get it out of the way. And that way you get your whole Saturday sorted. Okay, so let's recap. So we wanted to do the balance now, assuming that A1 wasn't there and assuming that B0 isn't there. So this is your case A3. And in case A3, you assume that A1 is equal to 0 and B0 is equal to 0, and that leaves you with 3, 4, 5. And we had discussed that the most obvious balance is to do a 3-4 balance if you have 3, 4, 5, because you don't typically think of that cubic as coming into the game. So you balance 3 and 4 together, and you assume that's bigger than 5, 6, and so on. And that gives you one fixed point approximation where x is like minus b2 over b1 times mu. And this exists for all mu. I'm being a little bit cavalier when I say for all mu here. I mean both negative mu and positive mu, but only near mu is equal to 0, because all these arguments are only near mu is equal to 0. And that left you with the last, but this turned out not to be the only possible balance, because you can have a 3-5 balance. So you can have a 3-5 balance in this problem, and that turns out to be much larger than 4. And so if you just check 3 balancing 5, you have C0 times x squared. I cancel the x's because I'm going to ignore the root nu is equal to 0, and I have minus b1 times mu. And then you simplify that, and that tells you x is twiddles the square root of b1 over c0 times mu. So mu to the half. Yes, that's right. So in the dominant balance, you always ignore the sign. So when you talk about what is in balance, you're just talking about things being either magnitude of that thing being large or magnitude of that thing being small, so 0 or infinity. But when you form the approximation, you're basically saying, if, for example, if I do balance 3 and 5 together, you're saying x1 x times mu plus c0 times x cubed is approximately 0, and then you do move it over to the other side. So the dominant balance ignores signs, but then you get an approximation for the main equation, and you do need to account for the positive or negative that way. Does that make sense? Okay, and we verified in the last lecture, if you don't remember, you can go back, that this was a consistent balance. And you can go on and verify whether or not, for example, 4-5 is a legitimate balance, and you'll come to the conclusion that it isn't. That these two are the only balances of relevance. Okay? This one here looks like a line. This one here looks like, so this one depends on if this quantity here, minus b1 over c0, is greater than 0, then mu greater than 0, it exists for mu greater than 0. But if this quantity is less than 0, then it exists for mu less than 0. So the point of this guy only exists on one side of mu, on mu greater than 0, mu less than 0, depending on what this number is, whereas this one here exists for all mu. Do you mean, why did you ignore this x and the x cubed? I think I canceled it on both sides. So I had an x cubed here, and then I canceled this x here. Okay, so that's all fine and good. And so the local bifurcation picture that you get so it exists for mu greater than 0, mu less than 0. So the local bifurcation picture that you would get, this is mu here, this is x here. Here this looks like a line, and it's a line of some gradient depending on what that number is. So it might look like this. If this number is negative, if minus b2 over b1, if b2 over b1 is negative, then this whole thing is positive, and this looks like minus b1 over b2, b2 over b1 times mu. And these guys essentially look like arms, right? So they look like one arm like this and the other arm like that. Okay? So this is a plus arm and this is the minus arm. And it only exists on one side. And so just so that this graph isn't confused, I'll remove this line here, remove this line here. So this is a pitchfork. Okay, it doesn't look like, so it only looks like that in a neighborhood of the point, right? So for instance, after a while, you'll notice these two graphs may intersect, but because this is just a local analysis, you're not worried about that. You're just looking at a zoomed in region near that origin. If I'm balancing things, then yeah, so in theory, when you balance things, or you use this less than, much greater than, or tilde sign, you're always talking about a particular limit. So you have to say it's much less than this thing in a particular limit, as x goes to 1, as x goes to infinity, as x goes to 0. In this case, we haven't mentioned it because from the get-go, from at the start of chapter 5, it's always assumed that this is tending to 0. Does that make sense? Okay, good. All right, let's do a canonical example of this. And there's kind of two canonical examples of this. There's actually two types of pitchfork bifurcations. Before I do that, I just want to write down one conclusion here. So this is an example of a pitchfork bifurcation. So this case is a pitchfork bifurcation. And a pitchfork bifurcation is something in which you have basically 1 to 3 fixed points. You go from having 1 to 3 fixed points. So 1 to 3 fixed points. Or 3 to 1, just depends on which direction you're looking at. And the pitchfork bifurcation is divided into two types. You have subcritical pitchfork and supercritical pitchfork. So let's look at an example at a supercritical pitchfork bifurcation. So I haven't done this very well in the last couple lectures, but again, just to tie this in with where we are in the lecture notes. So this was the dominant balance for the pitchfork bifurcation. Here on the right, x, this is the mu, x behaving like mu solution, and then you have the x behaving like mu to the 1/2 solution. Oops. So here's the x behaving like mu to the 1/2 solution. And so now we're going to go and look at a canonical example of a pitchfork bifurcation. And the illustrations are already in the lecture notes, so I'm going to just do it with MATLAB rather than drawing it on the board, and we can kind of see how it works. Also, just to remind you, so those of you who did go to the MIGS, we got you set up with the MATLAB Drive folder, and I'll just show you the folder here. And in that MATLAB Drive folder, I'm going to begin dropping in the codes for those lecture notes. So we're currently in lecture 9 here, and you'll see we have an example of a supercritical pitchfork, which is the top one, unlabeled, and then the subcritical pitchfork. So let's open up supercritical pitchfork and then see how it works. So this is an example where your cubic is given by this equation here, 1 plus mu times x minus x cubed. Okay. And so this is this equation here always has x equal to 0 as a root, and it has well, let's not do it all with math. I realized we should do this on the board first. So let's look at this example. And this is our supercritical pitchfork. And the equation, the f that we have is 1 plus mu times x minus x cubed. Okay. So the analysis is always the same. Let's go and find our fixed points. Let's go and check stability, do a couple cobwebs, and by then we should sort of know how we should plot the bifurcation picture. Okay, so step one, let's find our fixed points. We've got x is equal to x plus mu times x. I'm just going to expand this out here, minus x cubed. Okay, so we get to cancel our x's from both sides, and this leaves us with 0 is equal to x times, in brackets, mu minus x squared. So x equal to 0 is a fixed point, and x equal to plus or minus root mu is a fixed point. And as always, when you get your fixed points, just make sure that you state the region in which you have the fixed points. So this is for all mu, and this one's for mu greater than 0. Okay? Once you've done that, then go and find stability. And to check stability, you just take the derivative of the function and then substitute in fixed. So here, check fx. Fx is equal to 1 plus mu minus 3x squared. So, and just check all the points. So you've got fx at 0. That's 1 plus mu. So this will be, so x equal to 0 is, so if mu is less than 0, then that's less than 1, and x equal to 0 is stable. I'll call it S if mu is less than 0. And if mu is greater than 0, then this is greater than 1, so this is unstable. Okay. Then we've got our second fixed point. We'll do both of them together, I guess. We've got fx at plus or minus mu to the 1/2. That's 1 plus mu minus 3 mu times mu. So that's basically 1 minus 2 times mu. And you just have the opposite conclusion. So if, I'll do it in the same format as here. X equal to, I've got x equal to plus or minus mu to the 1/2 is, it will be stable if mu is greater than 0, and it's unstable if mu is less than 0. Okay? So you sort of know enough actually just to plot the bifurcation diagram in all its glory. Here's your mu, here's your x. Firstly, you know that x equal to 0 is a fixed point. So in fact, this axis is itself a fixed point. You know it's stable on the left, it's unstable on the right. So on the right here, you're going to make this guy dash. You know when I say guy, I mean the gender-free guy. Person. I don't think of guy, male. So x equal to 0 is stable on the left, unstable on the right. And also, you've got two arms coming out. You got one arm which looks like a root mu to the 1/2. And you've got another arm and they're both stable. Okay? So you have this supercritical pitchfork bifurcation. The way I just think of supercritical, I know it's probably not a very good way of remembering it, but I just think super, so it's got two tines, two stable tines. So these are my 3 tines of the pitchfork. If you got 2 stable tines, then it's super. If you got 1 stable tine, that's the subcritical that we're going to look at in a minute. That's sub versus super. Okay. All right. Let's look at an example. So this is we've got 1 plus mu times x minus x cubed, and we're going to put in a negative value of mu and then plot it, and then we'll put in a positive value of mu and then plot it and kind of see, well, how's it all turned out. So in this negative value of mu, you notice that there's only one fixed point, right? Only x equal to 0 is a fixed point of the system. And if I start anywhere, so for example, if I start out here, for instance, actually before we do that, notice that the x equal to 0 fixed point, you know that it's unstable. You know that it's stable because the gradient here is shallow. It's a shallow gradient compared to the gradient of the dashed line. So if I click anywhere here, you should notice it tending to 0. Okay, and if you click somewhere else here, you should notice it. Okay, good. So now you're going to start changing your cubic, and as you start changing your cubic, eventually these minima and maxima will go up or go down and go up respectively, and you'll end up with 3 intersections instead of 1. So 0.5 here. Let's go a little bit closer to so we see how it works. Okay, so we've just crossed the mu is equal to 0 threshold, and at that point you've gone from one fixed point which lies at the origin, and now you've created 2. Notice that when you do, let me just close this cursor for now. When I create the 2 fixed points, the one on the left is somewhere over here where my mouse is, and the one on the right is somewhere over here where my mouse is. When you create those 2, they come out of the origin, right? So if I want, I can go a little bit closer. Well, I'm not going to run the code, but if I wanted to, I would diminish mu a little bit closer to 0, and you'd see this fixed point and this fixed point emerge from 0. And that's what you see. That's what you're seeing from this picture. You have 0 fixed point, and then the 2 arms of the other 2 fixed points will emerge from x equal to 0. Okay? And if I were to click, let me run this with a slightly larger value so you can see the stability. Again, when you do these graphs on the computer, you should be able to judge, or you do them by hand if you're careful by hand, you should be able to judge the stability just by looking at the picture. Firstly, notice from the origin here, now you have a steep gradient. So you're expecting the origin to be unstable, whereas with the 2 arms of the pitchfork, these have a shallow gradient, right, compared to the line. So what you should notice if you click and do your cobweb is that it should move away from x equal to 0, and it should move towards the secondary fixed point. Okay? So this is our supercritical pitchfork. The supercritical pitchfork that goes from 1 time to 3 times, from 1 stable to stable, from 1 fixed point to 3 fixed points. Okay? And then the subcritical pitchfork is just obtained by applying a sign difference to this cubic equation. Is everything okay? So I'm asking, is everything okay? Because my video froze and, okay, good. My video froze and I was a bit unsure whether the stream was actually still active or not. Okay, so for the subcritical pitchfork, you have 1 plus mu times x plus x cubed, and you can just see the notes for the analysis. But actually, there's this is invariant under a sign change, right? Or so just note, sorry, it's not invariant, but it's asymmetric under a sign change. So note if x tends to minus x, we recover a similar equation. But the stability is slightly different. It'll be a little bit easier if I just look at do the simulation. I'm sorry to hear that. Okay, So let me show you what the subcritical pitchfork is doing, but the analysis is essentially the same. You're going to go find your fixed points, just study the gradient, and just check where that gradient is less than 1 or greater than 1. So we're going to run the subcritical pitchfork again with a negative value of mu and just see what it looks like. Okay. So now when mu is less than 0, you'll notice you have 3 fixed points rather than 1 fixed point. You've got 3 fixed points. The gradient on the left one is steep, so you're expecting this to be unstable. The gradient at the origin is shallow, so you're expecting that to be stable. So if I click my mouse somewhere here, what should happen is that you're going to move away from the left fixed point and move towards the center one. Okay? So this is already telling you that the bifurcation diagram for the subcritical pitchfork should have 3 tines when mu is less than 0, and that the 2 edge tines, the first and the third ones, should be dashed, not solid as they were, and that the center one should be solid. Okay? And then now if I go to mu equal to 0.5 instead of negative 0.5, okay, then now the former 2 roots have disappeared from there. They've gone down, and at mu is equal to 0, they disappear. You don't have an intersection anymore. But the center one now, you can see that it has a steep gradient, so it should be unstable. So if I click my mouse here, it should move away from the center and go off to it. Okay? That's the basic idea. So in terms of the bifurcation diagram for this picture, what does it look like? Well, we firstly, in the numerics, we firstly investigate the case where mu is less than 0, and you remember there were 3 fixed points on that. And you also remember that it was unstable from the left tine, from the left fixed point, and it should be unstable from the rightmost fixed point, but stable at the center. So you're expecting the center to be stable, and then unstable afterwards. And you're expecting the first and third tines of the pitchfork to be unstable. So this is your supercritical bifurcation. Subcritical bifurcation. And good practice to write your pitchfork PF, pitchfork bifurcation. Okay? So that was just the memory device I kind of told you before. Supercritical, it's super because it has 2 stable tines on the right. 2 stable tines, and then it's subcritical if it only has 1 stable tine. So 1 stable tine. Okay? The direction that this happens, by the way, so you notice here that we've gone from 3 to 1. Okay? The subcritical or supercritical, or indeed any bifurcation analysis you do, it doesn't depend on the direction on the side this happens on. So I would still call a configuration where I've gone from dash to solid, and then 2 dash pitchforks. This would still be a subcritical bifurcation, even though it's happening in the other direction, right? It's more about, it's invariant to a rotation of the picture. So the subcritical part of this terminology only refers to whether you've gone from an unstable to 2 unstables, or whether you go in the supercritical case, you have 2 super because you've got 2 solid tines, and then unstable and unstable like this. So this is supercritical, this is subcritical, and I can always rotate that picture and it would still have the same classification. Okay? All right, and that's basically it. So that's our analysis of the 3 types of case A bifurcations: saddle node, transcritical, and supercritical. The last thing of this chapter is basically just to tell you how you call these different separations of these bifurcation cases. And that brings up the terminology of codimensions. I'll write down the terminology of codimension. Someone's calling me. Well, I'm going to ignore that. Codimension is a measure I don't know whether you can hear that. There's a phone ringing in the background. Codimension is a measure of typical number of elements, typical number of conditions constraints or conditions required in the Taylor series in order to see the bifurcation. Okay, so our bifurcations include, let's make a table of this. Okay, so we're gonna do a little table here. We're gonna have a bifurcation on this column. We're gonna have fixed points on this column here. We're going to have codimension on this column here. You'll get the idea of what codimension is after we write it down. And then we're going to do a little diagram on this column here of what it looks like. Hopefully I have enough space. Okay, so the most basic one we looked at was saddle node. Okay, and in that case, you went from 0 to 2 fixed points. And the diagram looked like this. So you basically had your little axis. And one was stable, and one was unstable. That's your prototypical saddle node bifurcation. In this case, the codimension was just 1. 1 because the only requirement on this was that fx was equal to 1. This was in fact the requirement for case A. This was the only condition. So if fx is equal to 1, then the number that you had here, which was an a0 times x, that a0 had to be 1. So there's only one generic constraint on this problem. Now, when you talk about codimension, you're talking about strong constraints. So, for instance, this A1, it can't be equal to 0 in order for you to have this condition, but you don't count that as part of the codimension. The other way for me to explain that count, the count that you do, is that you remember that when you derive some of these quantities, you had square roots. You had square roots of B2 over B1 or B2 over B0 or things like that. If any of those square roots have zeros in the denominator, then it won't give you a fixed point, but that as well is not counted as part of the codimension. Then you have the transcritical. And in the transcritical, you went from 2 fixed points to 2 fixed points. It was just 2 lines that cross, but their stability changes. So the picture of the subcritical bifurcation was basically you had a line that went from a solid to a dash, and then a dash here into a solid like that. That was your TC. By the way, just always get in the habit. I've not been doing it very well. TC and then SN for saddle node, TC for transcritical. And in the case of the transcritical bifurcation, the codimension was just 2. So you've got the former condition of fx equal to 1, and then you've also got the additional condition that f mu was equal to 0. this f mu, by the way, I'm writing it in terms of the derivatives, but you just equate them to the first term here. So this was A1 equal to 0. That was the condition. So for the transcritical bifurcation, you needed A0 to be equal to 1, and you needed A1 to be equal to 0. Okay. Now finally, you have the pitchfork bifurcation, and then those yielded the two cases. I'm going to do my table up. I have to bring it up to the first row here. So the last one we looked at was the pitchfork, and that went from 1 to 3. And remember that direction doesn't matter, so you say 3 to 1 or 1 to 3. And here again you say 0 to 2 or 2 to 0. So this picture can be flipped around, and it's still a saddle node bifurcation. In that case, you have a codimension of 3, and the conditions were that fx is equal to 1, f mu is equal to 0, and f mu mu is equal to 0. So this was these two conditions here were A1 is equal to 0 and B0 is equal to 0. And that yielded a picture of super because it's got two super tines. This was your supercritical pitchfork bifurcation. And then not super, subcritical, you've got two unstable tines on the right here. And that. This is your subcritical. Okay. So notice that we can end the game. We don't have to end the game here. We can keep on going. And the deeper you go into the series, the higher this codimension gets, the more restrictive it is. So basically, the more rare you would see it, because the higher number this codimension is, essentially the more restrictions you're putting on your function. It has to be a function that has all these different properties. But you can go deeper and deeper and continuing to derive more and more conditions. Any questions? Sometimes it takes a while for you to sometimes it takes a while for the theory to sink in, and you don't have any questions right away. You might have questions a little bit later. Okay, so we've got 5 minutes left, and in the last 5 minutes, I just want to talk about one of the problems from problem set number 2, the one that most of you have handed in already, but someone had asked a question about wanted a bit of a hint of getting started on one of the questions. So let's just talk about one of these problem set number 2 questions. Go to. So the question was essentially about this function, this number 1. Let's read the question together. Consider the map xn plus 1 is equal to mu times e to the x. This is your f. Where mu is a non-zero parameter. Sketch graphs of f for both positive and negative values of mu. Okay. Find values of mu at which the fixed point undergoes a saddle node bifurcation and a period doubling bifurcation. Use the graphs for f to infer stability. Sketch a bifurcation diagram for the map using solid lines for stable and dashed lines for unstable. So I think where people got stuck, well, I mean, most people could draw the bifurcation diagram for this. To draw the cobweb diagram for this, but we'll do it as well together. But where most people got stuck was essentially how to get the fixed point and how to get the style node and the period doubling bifurcation. Because this was an example of a problem where you can't actually solve for the fixed point in closed form. Okay. So this was a question where you had f of x equal to mu times e to the x. And as a first go, look, the department got me a new ruler. Where all your 9,000 pounds a year is going. state of the art. But okay, so my tip when you do cobweb diagrams is to always plot different limits until you understand them. So by different limits, I mean here you have to plot mu greater than 0, mu less than 0. Plot them for the two limits of mu being small and mu being large. So I always give the tip of plotting, in this case, 4 different mu's. Mu small and positive, mu large and positive, mu small and negative, and mu large and negative. Would I recommend quality or quantity on problem sets? That's a good question. I think you would recommend quality if you intend to do the question, but you would recommend quantity if there's a place in the problem sets where you're stuck. You don't want to just not do anything because you can't get over this place. So you want to go on to the next question and do enough of the next question to basically think, okay, I know what's going on, and I'm going to get those little small issues. On the other hand, you don't want to not do enough so that you don't understand. So you have to have enough quality, if that makes sense. Yeah, exactly. So I think Kay Anders' advice is exactly what I would say, that you want to do fewer questions well, but at the same time, you have to do enough so that you get a taste for what the course is about. That means you pick up some of the questions you didn't do. Okay, so in this case, let's do the case when mu is small. So you know that this thing here always has an intersection. You know that at f of 0, it's just mu times e to the 0, which is mu. So the y-intercept here will move down as mu gets smaller and smaller. When mu is the smallest here, let's look like that. Sorry, what am I doing? I'm doing exponential decay, not exponential growth. Okay. So when mu is small, you have this. And you can be assured that there should be 2 points of intersection, one on the right and one that comes out of the origin. Okay. Now eventually mu, so this here is our mu greater than 0 and mu small. Now eventually mu gets to be very large. It moves up this y-intercept, but if mu is very large up here, okay, this is the mu large case, mu greater than 0, mu large. Okay. Now the other thing that you should be assured of is that if mu is greater than 0 and small, then this gradient here will always be shallow. It'll always be small. It has to be greater than the axis, right? And so it's always going to be less than that line. And so you know that certainly this guy will be stable. This should be stable. On the other hand, this one here, if mu is very small, then it's going to take a long time for it to ramp up, right? And so this will have a big gradient. So this has got to be unstable. That. Okay. Now, on the other hand, if mu is less than 0, then this thing flips. Okay, and again, you have the case here when mu is less than 0 and mu is small. But in this case, there's no difference between when mu is small and when mu is larger. Well, not quite. As in, there's no difference in the number of fixed points. You always have one fixed point here and one fixed point here. When mu is extremely small, if this was extremely small mu, then you have to be really close to the axis, right? And so this guy here has got to be really shallow. So you know that this guy has to be stable. But on the other hand, if mu starts to increase, you're going to get your intersection a lot later, and this gradient here will get more and more steep. Eventually, this gradient has to exceed -1. and you've gone to unstable. Okay. Right. Well, just from this picture here, you can kind of make the bifurcation diagram just from this picture. I'm sorry, I'm going over time, but well, you can be free. I'm gonna wrap up this. Just from this picture here, you can make the bifurcation diagram, or you can get a guess of what it has to be. Okay. Firstly, let's talk about mu greater than 0. You know that when mu goes to 0, this fixed point here tends towards the origin. So you know that it has to come in like this. Okay? You know that it's stable, so it's got to be solid. You also know that when mu is less than 0, it's moving this way. It's moving, you see, in the direction of this arrow here. So it's got to be stable both sides of the origin. So it's got to do something like that. Okay, now you also know, this is a lot harder to visualize here, but you also know that when mu is tiny, right, this fixed point, where is it? Where it's well over to the right, because it's taking a long time for that graph to ramp up, right? So you know that this fixed point here has to be up there somewhere, right, for positive infinity. And you also know that that fixed point there has got to be unstable. Remember, because the gradient is so big. So it's got to be doing something like that. You also know that when mu gets to be larger and larger, eventually this guy will move up past the dashed line, and you have this picture here. So at some point, I don't know where, this, at some point, sorry, just make sure here. Yeah, sorry, I've completely misunderstood. Lost my train of thought for a second. So at some point, you know that this curve will move up, and you'll have no intersections. You see this curve here, no intersections. So after some point here, you know there has to be nothing. Okay? This is harder to see, but the other thing you would argue is that as this curve moves up, right, this intersection point, the one that was really close to the origin, will creep towards the right, whereas this one will creep towards the left, and these two will join together. See? So this is a bifurcation point, and it's got to be a saddle node bifurcation point because you have 0 on the right and 2 on the left. You don't know that the graph looks like this, you know, the particular shape, but you kind of know at least that it's got a dashed line way up at infinity, and you fill in the rest of the curve. This is the place that students get really freaked out because you know, it takes a little bit of guesswork to finagle and realize, okay, the curve looks like that, and it's not an exact science. But the point is for me to go through the intuition of how you figure it out. And you can fill in the curves, you can fill in the gaps however you like. Okay, what about on the left? Well, on the left here, when mu is on the left, this fixed point begins to creep down, right? It moves down, moves down, moves down. But eventually, it goes unstable. Moreover, you know that it goes unstable when the gradient is -1. So here, the gradient is 1, is positive. So this guy's got to be case A. These will be case B. These will be the period doubling bifurcation. So in this case, you have a period doubling bifurcation, and you'll guess that you'll have 2 arms coming out corresponding to that period doubling. But this, you don't quite know. This is just guesswork at the moment. You have yet to do the analysis that will show you that period doubling bifurcation. This is just guesswork. Okay? All right, so this is what you can glean just from a basic cobweb analysis of the problem. What about our ability to actually solve for these bifurcation points. Why is that so tricky, right? So you've got f is equal to mu times e to the x. Let's solve for the bifurcation point. Let's solve for the fixed point first. Then we solve for the bifurcation point. So the fixed point is at x equal to mu e to the x. And you're screwed at this point because you can't solve the equation because there's no closed form solution to that equation. So that's all you can do. So no closed form solution. But there exists there exists a fixed point based on graphs. So you don't have a way of explicitly solving this, but based on the way that you drew the y is equal to x line, then you drew the various exponentials, at least you have the intuition that there has to be a fixed point, more than one. The question has been asked of how would you compute the formula for the arcs in the period down bifurcation? That's part of chapter 6. So in chapter 6, you develop an approximation, but in terms of this question here, there was no expectation for you to go and find a formula for it. You just basically draw it in, you sketch it in based on this is what I expect. If you want, the other way of doing it without the chapter 6 theory, without doing the local approximation, is that you actually do explicitly solve for the fixed points. And in that, for the period doubling bifurcation, in that case, you have to solve the equation x equal to f squared of x, right? But you probably can't do it. You can't do it in closed form. So the basic answer is the chapter 6 theory will tell you how to draw the little picture around the point. If you want to draw the point the arc everywhere, then you either have to do it numerically or you have to be lucky enough that you can actually solve the problem. So you can't go any further at this point, but let's solve for the bifurcation point in addition. So in addition to this condition, let's call this x star, if I want to call my fixed points x star. Though I think in the notes I called it x naught, so I'll call it x star here. So a fixed point x star is something that satisfies that equation, and a bifurcation point is something that satisfies that equation there. And so you can't solve for the value of x where this happens, this fixed point, but you can solve for both of these. Okay? So I can take the derivative fx here. That's mu e to the x. And I need this to be equal to plus or minus 1. Let me call this x star, where this happens. Okay? And then I can combine this equation 1 with this equation 2. So x star has to be firstly equal to plus or minus 1. Just equate this one with this one. So this should be minus 1. Well, we haven't quite checked that. This should be plus 1. And then you substitute this guy into one of these two equations, either this one or this one, to get the value of mu. And thus, if I put it into, say, this equation here, let me put it into this one here. So you have mu times e to the 1 is equal to plus or minus 1. So that tells you mu is equal to either, it's either e to the minus 1 or it's minus e to the minus 1. I feel like I done something wrong here. Hold on, give me a second. Sorry. So when I put in the plus or minus 1 here, there should be a plus or minus, what I've done wrong. And then I move it over to the other side. So if I have a plus 1, I have a plus 1 e to the minus 1, but this should be minus 1 e to the 1 instead. Okay? So this intersection here, let me just conclude. I've got either 1 and then e to the minus 1, that's a 1 over e, or I've got minus 1 and e. So this point should be 1 over e, and this point here should be e. See, there you go. Okay, that's basically it. I'm sorry I've gone a little bit over time, but yeah, we've finished up chapter 5 this week. We've talked about the 3 different types of bifurcation: solid node, transcritical pitchfork. We also talked about codimension. That the codimension is the number of conditions you need to impose these bifurcation points. And we did a little table here of the bifurcation, the codimension, the fixed points, and the little graph. And we did this problem set example. So going into next week, we're going to look to finish up chapter 6 and then move on to more fun things. Okay, thanks everyone. Any questions? Feel free to ask. Have a good weekend. I think it's going to rain all next week. So enjoy the outdoors while you can. Thanks. Thanks. Can you have a bifurcation where one fixed point changes? Good question. Good question. I don't know. Don't know the answer to that question. If you have one bifurcation point, you just have an intersection, and then it changes stability. So the gradient goes from being shallow to being steep. And I feel like it's one of those questions that's either really simple, and there is a very simple example of it, or it's actually not that simple, and you actually have to go to very high codimension to get it. But you can have a think about that question. I'll have a think about that question. Maybe I'll come up with a better answer.